Welcome to AI Paper Swap. Today we are doing a deep dive into a paper from UC San Diego called Failure-Aware Causal Training for World Action Models, or FACT.
Yeah, this is a highly anticipated one.
Right, so if you were building vision language action models, WAMs, here is the core insight you need right away. Current world action models are severely bottlenecked because they are trained almost exclusively on successful expert demonstrations.
Exactly. They only ever see the good stuff.
Yeah. So when a robot takes a bad action in the real world, the internal model just hallucinates a successful future anyway.
Which is a huge problem.
Totally. So FACT fixes this by flipping the architecture to an action-then-future causal sequence. It predicts the future video and a task progress value, but strictly conditioned on the executed action.
So you can finally feed failure rollouts into your training pipeline.
Right, exactly. You supervise the world model to learn the consequences of bad actions while selectively masking the action imitation loss. That way your policy doesn't actually learn to replicate the failure itself.
Which is brilliant. You get way better policy success, plus an actionable progress predictor that can actively rank candidate actions at test time.
It's so smart.
Yeah.
But to really get why standard WAMs fail at this, we have to look at the structural flaw, right?
Yeah, we are basically stuck into dominant but, highly flawed paradigms right now.
Let's break those down. We've got video-first systems on one side.
Right, like Dream Zero. Those operate by generating a sequence of future video latents first. They literally imagine the visual outcome.
And then they try to recover the required physical actions to get there using an inverse dynamics model.
Exactly. But the critical issue there is latency. Your inverse dynamics model is trying to extract an action vector from a visual representation.
Which takes forever.
Yeah, and if you try to extract an action from a noisy latent space before the diffusion process is finished, the action vector is basically random noise.
So you need that future video to be almost entirely denoised before control even starts.
Right.
Which means if you were trying to run a high-frequency control loop on physical hardware, waiting for a 50-step diffusion process just to move a gripper 2 millimeters is, well, it's completely unviable for dynamic tasks.
It's way too slow. So the alternative is the conditioned future paradigm, which tries to bypass that latency.
Like Bagel VLA.
Right. Those predict future frames as auxiliary conditions for the action prediction. They happen in parallel to guide the generation.
But both of these paradigms share this hidden fatal flaw, right? The success bias bottleneck.
Because, like we said, they train entirely on pristine offline expert data.
They only ever see physically correct futures.
Paired with optimal actions, exactly. The data set is just humans or perfect oracles completing the task.
Right.
So think about what happens at test time when the policy drifts and outputs a bad action. Say, closing the gripper too early. The world model has no reference class for failure.
Oh, wow. So it just looks at the bad action and still hallucinates a success-biased future.
Yeah, it imagines the object being picked up even though the gripper completely missed it.
It's like training a chess AI entirely on grandmaster victories.
Oh, that's a great analogy.
Yeah, like it knows exactly what a winning board state looks like. But if it accidentally blunders its queen early on, its internal world model has no idea how to predict the catastrophic next moves.
Because it's literally never seen a failure.
Exactly.
Yeah.
It just keeps hallucinating that it's going to checkmate in 10 moves while its entire position collapses.
Yeah.
So how do you feed a model failure data without accidentally teaching the policy to imitate those terrible moves?
That is the fundamental engineering problem. If you just dump failed trajectories into a standard behavior cloning pipeline, the policy updates its weights to map visual states to failed action.
It literally learns to fail.
Right. Standard architectures simply cannot digest negative data. And that leads us directly to FACT's architecture and this concept of the causal flip.
Going from future then action to action then future. Let's look at how they actually implement that under the hood.
Well, FCT uses a shared causal diffusion transformer, or DIT, which is becoming the standard for these models.
Yeah.
But this single transformer denoises three distinct things: action tokens, value tokens, and future video tokens. The innovation is in the specific sequence of those tokens.
Right. The order is highly deliberate.
Exactly. It starts with the prefix image, the current state, then the predicted action. Next is a specific ground truth action slot. That is followed by the value token, and finally, the future video tokens.
Wait, I want to pause on that token array. Having both a predicted action and a ground truth action slot feels redundant at first glance.
It does, yeah.
But it's the linchpin of the whole paper. Why do we need both in the sequence?
We need both to implement teacher-forced masking. In the attention layers, the value and the future video tokens are strictly conditioned to attend to that clean, teacher-forced ground truth action slot.
Oh, okay.
Yeah, they apply a modified lower triangular mask so the future video and value tokens are explicitly blinded from the noisy predicted action generated by the policy branch.
It's essentially like a driving instructor with dual controls.
I like that, yeah.
The student, which is the policy predicting the action, might swerve into the wrong lane. But the instructor, the world model, forces the car back using the ground truth slot to safely show the student, hey, if you had kept doing that, we would have crashed.
Exactly. It provides the consequence without letting the student actually practice the crash.
You are structurally severing the action generation from the consequence prediction.
Right. You are dictating to the world model. Assume this exact clean action was taken. Now tell me what the future video looks like and give me a task progress value.
Okay, that structural separation sounds great for pristine data. But bringing it back to our core problem, how does this actually let us train on failures without ruining the policy?
It all comes down to selective loss masking during the backward pass.
Right.
When it trains on a successful expert demo, all the loss functions are active. But when they feed in a failure rollout, which, by the way, they gather super cheaply from the model's own failed rollouts, for those failure trajectories, they apply a mask to the action imitation loss, the LAC loss.
Oh, so the model isn't penalized or rewarded for the specific bad action taken in the failure rollout.
Exactly. The gradients for the policy branch simply don't update for that step. The policy branch ignores it completely.
Wow. But the world model branch still receives full supervision.
Right. The transformer is forced to look at the bad action sitting in the ground truth slot, look at the failed future video, and look at the lowered progress value.
And it learns the causal mapping between them. The robot learns the consequence. Like, if I execute this trajectory, the grasp fails.
Yes. It learns the physics interaction without the policy learning that it should execute that trajectory.
That is brilliant. It turns garbage rollout data that usually just gets thrown away into high-signal consequence supervision.
Yeah, it's huge.
You mentioned the task progress value earlier. Let's get into that value head, because this isn't just a training stability trick, right? It's a crucial tool for deployment.
Exactly. The value token, the VT, represents normalized task progress. It's scaled from 0, the start, to 1, which is successful completion. And because Factate trains on a balanced diet of both successes and failures, this value head becomes extremely sensitive to the quality of the action it's conditioned on. It deeply understands when an action is going to derail the task.
There is a specific rollout trace in the paper for a PickCubes task that visualizes this perfectly.
Oh yeah, that graph is amazing.
You see the predicted value steadily rising from around 0.2 up to 0.8 as the robotic arm reaches down toward the target cube. It thinks it's doing great.
Right, the trajectory is matching the expert data.
But then there's a frame where the grasp slips. The gripper closes on empty air. And instantly, on the very next action step, the predicted value plummets down to 0.4.
That trace is the ultimate proof of failure-aware training. If the model had only seen successes, that value would have stayed artificially high.
It would have hallucinated that the cube was in the gripper.
Exactly. But because the world model knows what a failed grasp looks like physically, the value predictor instantly recognizes the consequence of the slip.
And the most impressive part of that trace is what happens next. The policy adjusts, executes a recovery behavior to re-grasp the cube, and you see the value curve climb right back up toward 1.0.
It's so cool.
So how do we actually leverage this at inference? If we were deploying onto physical hardware, how does the model actively use this value to prevent the slip in the first place?
Well, at test time, FSD operates in a two-stage inference process. In stage 1, the model simply denoises an action chunk. It predicts what it thinks is the right move based on the current visual state.
Right. But we obviously don't have a human expert providing ground truth at inference.
Exactly. So for stage 2, SAT takes that denoised action from stage 1 and plugs it directly into the ground truth slot. Then it predicts the future video and that highly sensitive task progress value.
And because that value head is so accurate at detecting bad actions before they play out in the real world, we don't just have to sample one action and hope for the best.
All right, you sample multiple candidate actions. The paper tests this with n equals 4 candidates.
So you run stage 1 4 times in parallel.
To get 4 different potential action chunks, yeah. Then you run stage 2 to get the predicted value for each of those 4 chunks. And finally, the system just ranks them and selects the action chunk with the highest predicted task progress.
This is wild. This is essentially bringing test time compute into the physical robotics space.
Oh, completely.
We've seen this explode in the large language model world with things like OpenAI's o1, where giving the model more time to think leads to massive performance leaps. Here, we are explicitly trading compute latency for physical reliability.
It is the exact same underlying philosophy. And let's look at the compute math. Single action inference for FACT-EOS is quite fast, about 380 milliseconds on an RTX 6000.
Which is perfectly viable for many standard control frequencies.
Right. Now, if you execute the n equals 4 candidate scoring, your latency increases because of the extra forward passes.
But the trade-off is your success rate jumps significantly because you're catching bad actions in simulation.
Before they break something in the real world, exactly.
Okay, so the architecture makes perfect sense theoretically. The masking protects the policy, and the value head filters bad actions. But theory is cheap in robotics. Let's talk about the sim and real-world benchmarks.
Yeah, so in the RoboTwin simulation environment, they evaluated across 50 different manipulation tasks. FAXI, code trained with failure data, achieved an 87.5% average success rate.
Wow. To put that in context, Pi 0.5 hit 79.8%, and Pi 0 was way down at 62.2.
Exactly.
I did notice a model called Modus slightly edged out FCT in sim, hitting 87.8%.
Yeah.
But there's a massive hardware caveat there regarding inference speed, right?
Huge caveat. Modus achieved that, but its inference latency is 1,220 milliseconds. FACT is hitting 87.5 at 380 milliseconds.
So it's delivering state-of-the-art performance at roughly a third of the latency.
That is the direct advantage of the action then future causal flip. You don't have to fully decode a massive latent video before generating your action.
Which is make or break for dynamic tasks. But what about the ablations? How do we know the specific teacher force masking is doing the heavy lifting?
The ablations isolate it perfectly. First they ask, what if we just remove the causal mask? What if we jointly denoise everything without that clean action condition?
And what happened?
Success dropped from 82% to 77%. The structural separation is clearly doing real work.
But the more important question is, what happens when you mess up the failure data handling?
Right. They ran an ablation where they added failure rollouts, but omitted the masking on the action imitation loss. They let the policy treat bad actions exactly like expert demos.
Oh, man. If they omit the mask, they're essentially doing standard behavior cloning on garbage data.
I imagine the policy just collapses.
It absolutely plummeted down to 63%. It catastrophically forgets the expert paths.
Wait, really? 63? Yeah. Think about how imitation learning works. The gradients update the weights to map a visual state to an action. If you feed it a failure state paired with a terrible action, the gradients get completely crossed.
The network literally learns that fumbling is a valid solution to the task.
Exactly. It proves mathematically that you cannot just throw failure data at a standard VLA model. You have to decouple consequence learning from behavior cloning.
Which is exactly what FET's loss masking achieves. That drop is wild. It really highlights how brittle imitation learning can be. But let's look at real hardware, because sim is easy. What was their physical setup?
They built a bimanual setup using 2 YAM robot arms, capturing visual states with Intel RealSense cameras, and to collect expert data, they used a Yellow teleoperation device.
Right. Jello is like a low-cost 3D printed proxy arm that matches the kinematics of the real robot. It's way more intuitive than a game controller.
Which is vital for bimanual data. And bimanual tasks are notoriously hard because the arms can hit each other, obscure the cameras,
What specific task were they evaluating?
5 scene tasks: stack cubes, pick cubes, handover, stack bowls, and a pouring task. Handover and pouring are especially difficult for success-biased models.
Because if the object slips even slightly during a handover, a standard model has no idea how to correct it.
Exactly. And the data efficiency here is striking. They only use between 50 and 200 expert demos per task, plus about 30 failure rollouts for the co-training.
That is a tiny amount of data. We're talking hundreds of trajectories, not millions.
But despite that, SAT hit an 89% success rate on those seen by manual tasks. For comparison, Modus hit 64%, and Cosmos completely fell apart at 25.
89% with less than 250 trajectories per task is phenomenal. But what about unseen tasks? Generalizability is the true test of a world model.
Right. They tested held-out variants with different object colors, shapes, and instructions. Vessi maintained a 77% success rate.
Wow.
And it remained highly competitive with massive foundation models like Pi 0.5, which hit 85%.
But keep in mind, Pi 0.5 is pre-trained on massive open-world datasets. The fact that FACT is punching in that weight class through a smarter causal training loop rather than just brute scale is incredible.
It's a massive validation.
So synthesizing all this, the researchers proved that the WAM paradigm doesn't need to be success biased. By reordering the tokens to action then future and applying teacher-forced masking, we can unlock an entirely new category of training data.
We can use all those discarded failure rollouts to build a robust world model without poisoning our policy gradients.
Which is huge.
It really is. And I'll leave you with a final thought to ponder. Right now, FACT-E uses failures gathered from its own model rollouts. But think about the broader implications for reinforcement learning from human feedback, or DAGGER.
Oh, man.
DAGGER is where a human continuously corrects a robot's drift. If we scale this causal training order to ingest massive amounts of raw, uncurated human data.
Data sets where humans constantly fumble, drop things, and correct themselves.
Exactly. We could build world models that intuitively understand the physics of failure just as deeply as the physics of success. What happens to robotic reliability when our foundation models learn not just from perfect trajectories, but from every single thing that goes wrong along the way?
A model that actually learns from its mistakes instead of just hallucinating that it succeeded. That is the holy grail for physical autonomy. Thank you for joining us for this deep dive into the FET paper on AI paper slop. Grab the link in the show notes, check out those value traces for yourself, and we will catch you on the next deep dive into the research.